Yes, so we are online and we're recording. Welcome everyone to this fifth session, the fifth module in our eLearning class for the Citiwatts tool in the OpenGIS for ET project. Today's session is going to be about the flexibility analysis in what-if scenarios, in a simplified energy system analysis tool in the Citiwatts platform. More on that later, what all those words imply. But yeah, the colleagues from AAU in Aalborg in Denmark, they have created this calculation module on energy system analysis, which we're going to present for you today. You know this overview by now. I suppose most of you have attended in the first sessions also, but we've dived into an introduction first and then looked into the heat planning tool chain, the district cooling aspects. Had a Q&A session on those exercises, and yesterday we also looked into the e-mobility and charging demand scenarios in the CMs on that. And yeah, today's session is about the flexibility as set, and then we're going to have a Q&A in 2 days and then another one in May. So please stay tuned if you dive into those exercises prepared for the inspiration on how to apply these tools. If you find questions there or curiosities that you want to discuss with the developers and so on, please stay tuned for the Q&A sessions in April and May. Today's session, again, it's going to follow the by now well-known module or agenda for the modules, with a brief welcome and wrap-up from my side, and then a little introduction on how the calculation module was developed, the background of that, diving into the calculation module, and then an exercise to demonstrate one way at least to how to use the tool. The team of organizers is still the same, so it's still Plan and E from Denmark and eThink from Austria, as well as the colleagues from Model 3 in Germany. And then today's technical experts are the colleagues from Aalborg University here in Denmark. Peter and Alison are both in the call and going to present the technical development and the exercise to demo it also and to test it. Yeah, just another one presentation of that. We have this Google Classroom, so if you want to see the recordings of other sessions and or see the exercises and so on, please check out this Google Classroom. That's where we gather all that information. I hope really that you got access today. You were struggling with it yesterday. If any of you are struggling with it, please reach out to us. The organizers, contact anyone you can contact, who would say, and then we'll figure out who answers. But you have the contact information from the login and so on. We'll figure out how to get you on board. Brief wrap up if anyone's the first session today. So just the wrap up that this project, OpenGIS for ET in the CES AeroNet framework with colleagues from Austria and Switzerland, Germany and Denmark. We've been developing and improving the hot maps tool in the Citiwatts tool. So basing on a solid ground and then updating and upgrading quite a bit. In feature terms, I would say we based it on a lot of developments on the heating planning, and elaborated that and improved that. There was added a district cooling tool that was demonstrated last week in the session, in the second module. Then the very basic mobility tool has been replaced by a new developed tool, containing 2 different calculation modules. And then there's also this integration of a tool for analyzing flexibility, which is the one we're talking about today. And in TRL levels, or the technological readiness level, we are going from some modules in 7 to a full platform in TRL 8. So just as done as it gets before it actually becomes a commercial product. The components and the products, so to say, in the OpenGIS for ET project are the platform itself, so the one that we are also demoing today, the browser-based tool, which contains on the one side the data sets, very useful information for energy planning on a large amount of different layers. Please refer to the first module for more detailed introduction to that. And then also the calculation modules, which are basically the calculators using those default data or your own data to then model certain aspects. Then we also on the side, we have the standalone tools, so you can either use the Python code so the pure code of those calculation modules to run it on your own machine, or you can also use some standalone Excel tools that we have prepared to basically wrap up and sum up those results from the calculation modules in the platform, because the platform basically gives you results on something, and then if you want to compare that across different aspects and so on, then you should make an overlay in Excel, and that's what we've been preparing for you. That's what those exercises should demonstrate, at least 1 or 2 or 3 ways to do so. And there's also a wiki to document it all, and then there's a demonstration and training and dissemination, and obviously the e-learnings here fall within that training part. Yeah, about what to expect on the Citiwatts platform, we have set a large amount of different data. That is about, for instance, demand data, but also about the building volumes and so on. Also some renewable potentials, which we'll come back to in a second. And then there's all the calculation modules, and this is just a gross list of what's available in there. You have seen some of these in the different modules, and today we're obviously talking about the one that is for the flexibility and energy system analysis, so the EnergyPlan CM. You've also seen something like this before. Oh, there's something with an illustration here, which we did not check. Of the struggles of reusing formattation. Oh, that did not work. Sorry, 2 seconds. Well, but the tool chain, or the workflow, as we call it, you have seen this before. But the whole aspect is that we have certain modules and certain components in the toolbox available on the platform, and you want to chain these different components together to make real analysis, because if you just click a button, then yes, something calculates, but if you want to make this an analysis that you can use for something, you of course also need to link those things together in a meaningful sense. And we have, for the different scenarios, for the different modules, tried to come up with some of these tool chains. So how to link some data and some calculation modules together, yeah, to a meaningful sense. And this would be that tool chain or the workflow for the EnergyPlan CM. You can see we only have one module this time, where we're actually looking into the calculation module itself. So it's not a chain of different calculation modules in this case, but what's important here is that we work with a lot of time series, a lot of different aspects within the energy sector. So many of the other CMs, they were sector specific, whereas this one is the one that tries to compile all those. So here we have a lot of background information that you can host, and that you can try and use, to enter more valid information into your CM. And the colleagues from Aalborg University will elaborate that in a second. And yes, obviously, if you want to talk about electricity production, you want to look into something about PV and wind potentials. That's something that you can also derive either from the tool itself or from other external data, and then using that simplified version on the toolbox to evaluate. And then also, as for the others, we have created this scenario assessment spreadsheet. So the for most of you, I suppose, a well-known format of Excel that we paste data into, and then we have prepared basically a template on how to use import and export functions of the toolbox to then get these data out of the browser and into your spreadsheet to further calculate with them. A final remark on those on the platform is, as the other times, please use this link to enter the toolbox. This is our map on the Citiwatts project. We recommend to use Edge. It also works fine in most other browsers, but that's the one that is like officially supported and also tested. And another remark is that some of the functionalities, I don't think it does apply for this very CM, but for most other functions, it's always a good idea to create a user, because then you get the upload and download, especially the upload function available, and a workspace in there. So please make sure to log in and register there. Something that I don't know if we made clear enough throughout the times, but there is an auto logout function, by the way, in the toolbox. We mentioned it at least once. Now I'll mention it again. But if you stay inactive on the tool for half an hour, then you will be locked out, and there is no pop-up for that. So please make sure that if you have left your computer for half an hour, that you simply refresh and make sure that you are still logged in, because otherwise your calculations may not be able to be used in your workspace, or you have to do them again once you're logged in. Well, that would be it from my side. With that, I would hand over to the colleagues from Aalborg. Alison, please.
Thank you, Max. Just a minute to share my screen. So yes, I think that everyone is seeing, right? Okay.
That's great.
So yeah. So hello everyone. My name is Alison Julio. I am part of the team in charge of the development of these calculation modules inside the Citiwatts platform. In the past couple of years, which was the duration of the project. This tool is destined to execute energy system analysis, which we'll dive deeper in a couple of minutes. But to get to the point today, I will give you a presentation of the concept and the application of this calculation module. Sorry, I have to jump on a few slides. Yeah, okay, sorry for that. The combination of Citiwatts and EnergyPlan was a concept to offer a novel and a scalable flexibility calculation tool in order to assist planners and decision makers in analyzing energy flexibility in specific areas under various hypothetical scenarios, what are called what-if scenarios. Given that we have a scope for this tool, and this given scope is to develop these what-if scenarios by feeding them with real data to evaluate the flexibility potentials of that decided and given area. The developed CM, therefore, enables the possibility to explore higher heat pump or electric boilers participation in heating networks. For example, increasing adoption of electric vehicles is another example, and the further integration of renewable energy in an analyzed energy system. And all that was done based on a tool that Aalborg University has been developing for 26 years right now, and is called EnergyPlan. EnergyPlan is a freeware software that has been, as I said, in development since 1999. It's programmed in Delphi Pascal. It offers to the user the ability to design energy systems using its own graphical user interface. This tool simulates the operation of any given energy system, calculates hourly energy balances across different sectors, such as electricity, heating, cooling, transportation, and industry. Besides focusing on the integration of energy systems and design of smart energy systems. In the flowchart, you can see all possibilities, all resources, and all sectors that EnergyPlan can dive into. And now, in the color ones are the ones that we used to develop the calculation module in order to achieve our goals with the project. So, what defines an energy system per se? An energy system is defined as a system with well-established boundaries that count with the energy flowing in and out to perform different activities. So in that sense, we can say that a PV panel is an energy system, a household classifies as an energy system, a city is an energy system, as much as regions, countries, and the whole continent. And with the aid of EnergyPlan, it's possible to assess from cities to continent all kinds of energy systems, accounting for all kinds of technologies and resources available within this software. And how the energy plan was developed and how it works. Energy plan was developed to perform analysis on national, regional, or even municipal level. It executes deterministic simulation-based. It executes a deterministic simulation, which means that every time you run a simulation with the same inputs, you have the same results. These inputs are based on libraries, which are to illustrate the scenario behavior, and there are on an hourly definition, which account even for the leap years, which means 8,784 data points. And then the outputs can be retrieved based on a strategic simulation approach, which can be determined inside the graphical user interface of an energy plan. So following to the CM development itself, the calculation module began with setting a straight connection between a virtual machine that was supposed to run energy plan and an API to promote the data traffic to move inputs from the Citiwatts platform to energy plan, execute the commands of running the energy plan, and then retrieving the results of that given simulation back to the Citiwatts. Following that, the proper code was written to handle a total of 27 inputs between basic and advanced, besides 8 distribution files, which are the libraries. And finally, the outputs of interest for flexibility and sector coupling analysis were displayed on the platform. Given that, the libraries for all countries were organized in a manner that allows the simulations to be possible for all NUTS levels on the Citiwatts platform. And finally, the results brought from energy plan were organized, displayed, including a chart presentation. So yeah, I think we can go to the inputs, and these are the most fundamental inputs. So I think it's important to pass through all of them with a brief explanation list. First, the wind power installed capacity is the first input. It refers to the capacity of the wind power installed in the systems which are subject of an investigation. This input can be found either on local statistics, on the reports, on institutions reports, international institutions reports, but also can be found within the Citiwatts platform through the CM called wind potential. Then it can be calculated for a given area, and then you can use that output as an input in the EnergyPlan CM. The same is valid for the PV installed capacity, which of course refers to the capacity of PV installed in the given system, which is subject of analysis. And the data for this input can be retrieved again from statistics or from a CM called solar thermal and PV potential within the Citiwatts energy sources category. Number 3 is the flexible electricity demand, which refers to the amount of electricity demand that cannot be moved from hour to hour. This is an input, important input on our calculation module, which also can be retrieved from statistics, but this one cannot be found on any other CM. The share of heat demand using individual heat pumps is the 4th input. It's supposed to be the share of total heat demand met by heat pumps in individual buildings. And this is a parameter that will depend on the scenarios the user wants to evaluate. Once the number desired on the future scenario for a share of heat pumps can be found on statistics, directives, reports, and etc. Following on the inputs, we have the share of heat demand using direct electric heating, which refers to the share of total heat demand met by direct electric heating on individual buildings. It's the same as the previous one, but this one refers to electric boilers, electric heating. And this is a parameter that has a similar approach to the previous one, which also can be found in different documents. Number 6 is the end user heating demand supply by district heating, which also has a self-explanatory name, is the end user heat demand met by district heating, and the parameter that can be retrieved from one of the CMs in this the Citiwatts platform inside the district heating potentials category of the CMs. This also can be found in energy planning documents, reports, and etc. The grid loss is the seventh input, which is the heat loss in district heating grids in the percentage of the total district heating production. This is an important parameter for district heating networks, and that can depend on the network's age and chosen technologies. A straightforward way to acquire such data is also through one of the district heating potential CMs that can be found on Citiwatts. Following to number 8, we have the next input, which is the heat pump electric capacity. Is the capacity of the heat pumps in district heating systems, and that's another technical parameter that can be taken from one of the district heating potential CMs. Okay, so the number 9 is the capacity of electric boilers, which is a similar one from the number 8, but again, referring to electric boilers. The number 10 is the share of district heating from non-electric units, which refer to the share of total heat demand produced by other units that are not heat pumps or electric boilers, like soil thermal, excess heat, and etc. And these numbers can be found on statistics, or it can be used as a decision parameter for future projections, given the diversification of the heat sources. Following to the district heating storage capacity, again, a self-explanatory title and a data that can be found on statistics. Following to number 12, we have the number of EVs, the total number of electric vehicles in the system you want to investigate. This can be found also within the Citiwatts catalog inside the CM called electric vehicles charging needs under the mobility CM category. So these were the first inputs, which are numerical, and then we got to the basic inputs, which are the distribution files. Distribution files within the energy plan are referring to leap year hourly resolution libraries with 8,784 data points for electricity production, which accounts for wind and PV in this case, inflexible electricity demand, heating, transportation, market prices for electricity. All these libraries are activated once you select a given country or region or municipality within the Citiwatts platform. It is important to highlight that if you choose a region or a municipality, it will be like inside the country, and therefore the library which is designated to that country, to that national level, would be applied to your region and also would apply to your municipality in a standard configuration. And this standard configuration came from a different project that an European research project called Synergies that was developed by the energy group on the sustainability planning department of Aalborg University. So if the user decides that other library would be more fit to the analysis, for example, if you are on a region, a determined region, that you think that it can be more fit to use another country, you can do that, and then just select which distributions libraries you want to use. So following to the advanced inputs, there are some really technical parameters here, like coefficient of performance for heat pumps, efficiencies, percentages of electric vehicles that can charge, and etc. The most important ones are the number 18, heat storage capacity per average day for heat pumps. Refers to heat pump storage capacity connected to heating in individual buildings. The heat storage capacity per average day for electric boilers. The share of flexible charge EVs that can send back to the grid when relevant, send electricity back to the grid. It's called vehicle to grid or V2G. The number 25, the charge capacity per vehicle. And the number 26, the battery storage capacity per vehicle. These are the most important one, but as I said, there is more, totaling a total of 27 inputs besides the libraries. Since I'm back on this tool chain workflow figure, to just reaffirm to you that it can be connected between the Citiwatts platform. You have several CMs that can be useful to use this EnergyPlan CM. And now I will pass the word, and Peter will start with the exercise. Do you want me to keep sharing, Peter, or is better to?
No, just I will share.
Okay.
Thank you very much, Alison, for the presentation of the tool. I hope you can see my presentation and my screen in general now. Excellent. So, as Alison said, this here is then the toolchain as Max also showed it here. So the toolchain is a bit different than many of the others because we are more collecting inputs for EnergyPlan from other tools to investigate different what-if scenarios. So in that way, EnergyPlan functions a bit differently than some of the other tools here. And what you need, you don't need all of them necessarily. It depends on your work, what you're working with, what scenarios you want to do, what you want to investigate. And in some cases, you might not need them. You could maybe continue with having other studies you use, or you have maybe some statistics you want to include. So that depends on your needs from different results to different results here. So for example, if you want to investigate a lot with electric vehicles, well, then the CM from EV density or the number of could give you a lot of information about the numbers of cars and the electricity demands for electric vehicles that then can be used to set up different what-if scenarios potentially with other things. So there's a lot of potential important discussions to have outside of what scenarios do we want to investigate in this kind of tool, because it's important to try out different scenarios, and that's where the tool has its strengths. It's relatively fast to do it, and it should be relatively simple to try out different approaches and see what the connections are. So in this one here, the exercise I prepared today is a fairly simple one, where we make a reference scenario for an area, and then we will try out 2 different scenarios and see how does that affect some overall metrics we have for the electricity system. And in it, I am actually only connecting to 2 of the tools because I have some statistical data I'm building on. So the 2 tools is the PV capacity one, so the CM solar, thermal, and PV potential, and then the CM wind potential for the potentials to install onshore wind power. So that's the only 2 tools I use in this. The other comes from statistics in it, but that doesn't mean you can't use the other things. You can use the other things. It's just in this case, I want to show some fairly simple and quick to show and explain scenarios. So we can also use some time on discussing the results. So here we first use the exercise. We focus on an area called Offenbacher mine in Germany, which has also been, as far as I understand, the topic of some of the other tool chains. So the first step when we make this and use these tools is to find some reference scenario, and it can be a historic year. It can also be a future baseline you have from another study or from some data you have, or some expectations you have. But it's important that we start out trying with a reference. So setting up a reference for a model, and then we can adjust and see what happens if we do different things. So here the reference scenario will be based on some energy statistic balance I have from 2022. From an Excel sheet, you can see on the right which data points are there. And for simplicity, we only assume that all electricity is imported to the reference scenario. So that is a simplification here, just so you know. I assume that there's nothing PV already produced there. That is, of course, probably not true. However, that's just to have a simplified approach to the scenario, so we can see what it means if we install the potential we can identify. So this is important to note that this necessarily doesn't show the actual current or the potential future as decided locally. This is more to show what is the capabilities of the tool. I will also not include all potential technologies we have. I'll focus on what we could call traditional electricity consumptions. So that would be in households. It could be computers, it could be lighting, it could be refrigerators. Typically, it's electricity demand where we assume that these demands are not flexible, meaning they cannot move in time. People will use that electricity when they have the need for it, and typically not wait for it. to be used. So that's what we call the traditional one, and that typically it's related to the current or a few years ago scenario electricity demand in total. Depending on where we are in the world, there could be quite a high potential electricity demand for individual heating or for EVs. So that depends on your current situation in your energy system. So that's important to have some ideas about what numbers can be used there. Sometimes it's national data can also be used as a guiding principle for local analysis in this case. For example, saying something about what is the typical consumption per person in a country. But in this case, we have something local available. Electricity consumption for individual heating, and you can also see the purple one on the right. So this is electricity consumption that's used either for heat pumps or direct electric heating. And you might not know what it's used for locally. So that's a bit up to the local knowledge and assumptions. And the issue here is that there's no necessarily statistical basis for that. It depends on what statistical availability you have here. So in this case, I assume simply direct electric heating for all of them, just to have it simplified. But some of it could be for heat pumps. And then we have electricity consumption for transport. So that will be mainly, here we will assume it's all electric vehicles or EVs, but it could also be electricity for having a tram running locally, or it could be a train system. So it doesn't necessarily have to be a car. It could be other forms of transportations here. And then we have some district heating production I've added here, which then is the purple one. The orange one. So these are the four I will include in this test or exercise. So first thing is to identify the area you want to use. And this here on the right, you can see is the Offenbach am Main. And then once you have chosen an area, you can go in and then identify and use the tool. It will be grayed out until you select an appropriate area. And it will also tell you what options you have there. And also when you have selected that area, that's very important based on these distributions that Alison explained. So once you have chosen an area, the tool will identify, okay, we are in this country. So these are the sets of distributions or hourly productions and hourly consumptions of electricity that we need to use, and also for heating. So that's important that you choose that. When you know that happens when you choose, and you can choose several at the same time. But if you do, it will use the first one that you have selected. But here we have only one area, and this is this Offenbach area. Then, based on the statistics, I have identified that these are the 5 numbers I need to insert. I don't need to insert more numbers for this exercise, at least in the reference scenario. So actually, this is sufficient for me to have a starting point for a reference scenario in this case here. So the first is this inflexible electricity demand. And that's what I called the traditional electricity demand before. So that is electricity demand where we don't expect to be able to move it around, so that the system cannot vary that from hour to hour, depending on the production of wind power and PV panels. So that's important to know, that this electricity demand will always be unchanged. It will never change from scenario to scenario. That's important to know here. Then I have added a share of heating demand used by direct electric heating. So you can see that's a smaller amount in this case here, but it's there, and it's important to include it also. This one can be moved around depending of the system you have set up. So if you add PV panels and wind turbines, the tool will actually try to make sure that the heat demand is sufficiently added and maintained using local, in the building areas, something you can define yourself, storage facilities, to move that load of electricity. So move when is it actually consume electricity to provide the heating. If you set 0 storage, that means it's inflexible. If you add a storage for heating in the buildings, it will be able to move it around. And that actually means that we can use more wind power and PV locally. Then is the end user demand by district heating. And you can see I've added a number here for that. And we will go into more of this because in the next one I have said that all district heating this is assumed to be from what we call non-electric units, and that is basically units where there isn't any direct electricity demand to consume. You're consuming when you produce the heat. So that means we don't have electric boilers and we don't have heat pumps. That's an assumption here in this case here. So that means that it comes from other type of sources in it. And then we have the number of EVs, and I have calculated based on the approximately amount of electricity there is in this, and then based on the standard default assumption I have in the tool for EVs, saying, okay, this is the amount from the statistics, this is the demand for electricity for transport. I can see it I have. Okay, I assume that then it's EVs, and with the standard assumption, that means it's around 6,200 vehicles. So that number is actually not directly statistics. It could be a different number of EVs, but that's to make sure I have the same and I have a reference I can compare to. Then if I then run the model, so if I can also go over to the tool maybe quickly and show it. Here I have put in the numbers here. So you can see here, this is 0.5 here and they're inflexible. I have when you open it first time, there is 100 here in wind power. You can remove that if you don't have 100, of course, and I will change it. It's simply there to make sure that if you run it, some numbers come out that's above 0. Then here the share of heating, direct electric heating. Then this is the end user demand for district heating. I can then adjust grid value, grid loss here for district heating. Here I just assume that default 20% is okay. And here then the share of district heating from non-electric units. I could also adjust the storage. I can just assume the default value here is okay. And then the number of EVs I have added here. And then you can see here, here you can change how flexible, how many of these will charge flexibly. So here I have a very positive, you can say from a flexibility point of view, assumption that all the EVs will try and charge flexibly. And that means that the tool would try to use as much of the locally produced wind power and PV that in the system to charge the EV. So you will actually see it in one of the scenarios that the peak of consumption for the EVs will actually change based on when we put in wind power and PV. And then we don't need to consider more. We can go through them all if we wanted to, but in this case, we just need to run it. So we can press run, and then you will get the results here on the right. And it takes a few seconds for it to run and provide the data. I have also run it in advance in case that could be an issue, but just to see here. Yes, so it comes here. And you can see here we have two options. We have indicators and we have charge. We will stay with the indicators first. The indicators are yearly numbers. So that's numbers related to some yearly ideas about the electricity system. We can see it's electricity consumption for heating. We can see what is throughout the year, what is the peak demand for electric heating. Here, the total demand for electric heating is very low. So that means this is 0. It's probably not 0. It's probably a bit above 0. But it just gets lost because the number in total is very small. And then we have from different individual here. And then here we have then how much do we use for transport? And what is the peak load of the transport sector? So that is the hour of the year where we most charge our EVs, electric vehicles here, 7. And then here is how much do we import of electricity, what is the peak of that import, so the highest hour, the hour we import the most. And then we can see export. We don't have an export, and it's the same for that with the peak. And then we can see some change in income if we sell some electricity, and then some cost if we import it. So this is based on some hourly import-export of electricity from this given area. If we take charge, you can see here our monthly data for it, and you can export the monthly here. You can see now it's only has some other demand, which is the traditional, the inflexible demand, and then a small demand for mobility. And we cannot even see here the demand for heating because it's very small in this system here. So that's just the tool of the overall. I'll then go through some of the scenarios. First scenario is where I've tried to add some more renewables. So I use the same setup for the reference as I've done before. And then I've used these two CMs I explained earlier to identify some wind power capacity that could be potentially installed based on at least the CMs, and some PV. Of course, these numbers might need to be double checked, but at least it gives some good indication to starting for this scenario. And then I add these two capacities in the tool, and then I run it again. So, and then I get, you can see on here the charts, you can see you both get some consumption, but you also get some production of coming out. And here it's clearly an area with not a lot of land area available for PV and wind in this case here. So there's plenty of consumption compared to production in this case here. So that's very clear for this. And we can see that PV mostly commences in the summertime, and we have wind mostly in the winter time. So we're actually in the monthly evens it out fairly in the year. And that's kind of the data you can play around with and look more into. And then also maybe it's very interesting to see if we look at our charge. Now I said it was 7 for charging transport before. Now you can see here on the right, it's 30 megawatt. And the reason it increased was we added PV and we added wind power. And then now instead of trying to export this, the tool will try to move that consumption to hours with a lot of production, so that we export as little as possible and use locally as most as possible. So that's why you see this increase in capacity. But actually, if you look at the import peak, it is 83 here with the renewables. It's here. And if you go back, you can see it was 84. So actually our import peak, how much we use our electricity connection to the surroundings, has actually decreased based on this, even though charging for transport has increased. And that's because it will also try to make it in areas where there is a high production, but also where there potentially is a low consumption in the tool. If we then try to look more into a different one where we try to keep the reference and keep the renewables, and then we say, well, what happens if we try to electrify our district heating system? And here I just added a sufficiently large electric heat pump to see what would happen. And you can see here that the electricity for heating that comes here in a dark, in between blue. So it comes mostly in the winter periods and a little small and somewhat smaller in the summer period here. And this one will also try to be flexible and use the storage that you have put in as available for it to try and use the most of the wind power and PV production locally first and foremost. Yeah. So I've added that heat pump, and then I've changed this share of district heating from non-electric units from 100% to 0%. So I'm telling the tool, you have to use the heat pump for all the electricity demand, for all the heat, sorry, not the electricity, the district heating demand. So it will only use that unit for it instead. Yeah. And you can get some inputs on that from the DH supply CM that's also in the Citiwatts tool to investigate that further if you need to. Here the focus is on the flexibility on the electricity system. Yes. We have also made a tool as Excel sheet, as Max explained, for helping comparing scenarios. So we have here, you can see on the right, it's the tool where you can put in the numbers, and you'll be able to download it from the Google Drive. And you will then be able to see some figures, and you can make your own also. So this here is just an example of how the figures could look if you want to make your own also, where we can see here the reference I made. I made then the scenario 1, which is then renewables, and then the scenario 2, where I then add the district heating, electrification of district heating. And here you can see, of course, the yearly electricity consumptions, and then the minus here is the import. And that's why it varies, because when I add renewables, of course, I import less into the system here. And then you can see that main one is in this cases here in flexible demands. And of course, we could play around with this and put more electric vehicles in, and that might change the picture again. Or we could go with direct electric heating for the district heating or individual buildings. So that could also change the picture. Another thing here is the peak electricity demands. As I said, that could also change around. You can see here the import peak here in the yellow. So for example, from reference to scenario 1, the import peak doesn't change a lot, as we also discussed a bit. So actually adding that renewables doesn't really change that import peak. But you can see here in some hours we have a higher peak for transport. So it could be relevant here to investigate, is this something that could be an issue for our local distribution grids, as EVs typically are charged on the lower voltage levels here. So this is just some tools you can use, and you can also set up your own graphs, of course. So I think that's it for me. Thank you very much for the attention. I hope you find it useful and interesting.
Yeah, thank you very much, Peter and Alison, for that introduction to the possibilities of this calculation module. Any immediate questions from the participants? There was one question during the presentation about which level to select the areas, but Alison already responded that NUTS 3 would be a good place to start for Offenbach. At least that's what your calculations were based on. Yeah, Peter already, or you both already addressed this whole scope discussion. So bigger the better, basically, for statistical data, of course. But it also makes perfectly sense to calculate effects on a smaller scale. So in this case, in NUTS 3 region, I would say. Doesn't seem like there's questions. Or maybe just put the remark then that well, we as consultants also use well, we don't use EnergyPlan that much, but I know it from from my study times. And of course, you can always dive into deeper into it if you want to use the tool as is, basically. But our whole approach in applying this tool also here in this toolbox is to basically show you some of the core features and initiate the discussions on these topics. So of course, energy planners, if you want to dive into the topics, you can also use the tools in their more advanced mode that goes for many of the developments that have been presented throughout these e-learnings. And EnergyPlan is one of those examples. But we hope to inspire you to maybe have an icebreaker on to look into these topics for your local areas also. And then as said so many times by now, the exercises are mainly one way to inspire you to apply them. But of course, please feel free to dive into them and also use them and apply them in your own local contexts and see what you can gain of analysis for that for your local areas. If there's not any more question, that doesn't seem to be the case, I would say thank you very much for the attention today. That was actually our last session or our last module on new features. Basically, from here, the plan would be that we again encourage you to check out the exercises presented and put as spreadsheets and slides in the Google Classroom. And if you have any questions or want to discuss the approaches that we have presented and so on, or whatever you may want to discuss, basically, we have these 2 Q&A sessions coming up where you will again meet us as presenters, but also the developers. There is a hand raised. I see, Lee, please.
Hello, can you hear me?
Yes, we can. Thank you.
Thank you. Thank you very much for the tutorials. I actually was absent the first 2 days, but I guess I can catch up by using Google Classroom. Thank you for giving me the access to the materials and the videos. I guess that the tool is still under development for further functions and so on. May I know how I can follow like just new updates for the tool when something is available, like who to contact or where to look at?
Yeah, we have a newsletter for this. Thank you for the question. We have a newsletter noting on the releases. Actually, the within the proper period, it should have been our final release already. But I'm sure we're still going to find a few small adjustments and so on. The project is officially ending in the end of August this year. But yeah, as of now, we will not add new functionalities per se, but there may be some smaller adjustments still. Yeah, but I actually don't know, Mijana, how can Lee enter the newsletter?
I have an email address, so I can just send the link to her afterwards.
It's,
Thank you.
in those newsletters, we also communicate the release notes and so on.
Yeah. Thank you very much.
Yeah, thank you. Any other questions? If not, I will say thank you and bye-bye, and hope to see you in the Q&A sessions for further discussions of the applications.